All right. So before we get started here, I just want to write a reminder at the top of this that this is the start of, we could call this the second half of Calc 1. Okay. And so this is wow, my handwriting is just really wonderful today. Okay, so this is the start of the second half of Calc 1, okay? And so we've spent the whole first quote unquote half of this semester talking about slope and what it means to get really close to sort of the distance between 2 points becoming really, really small so that we can find the slope at exactly 1 point. And so what I wanted to do before we got started here, but in the second half of the class, is do a little bit of a brain dump in terms of what we know. And so if I can have folks just in the chat, and you can send this to me directly, or you can type it out to the whole group, what are some concepts that we have learned so far this semester? And yes, Christina, you are correct. This is the beginning of the second half. It is not on this week's exam. Okay. Okay. So we've got a few ideas floating around here. We've got slopes. Gosh, we've got slopes. And yep, derivatives is a fancy word of saying slope. And so we've got sort of two kinds of slopes. How might we categorize those two types? Okay, so we've got a secant line, so slope of the secant line, and that would, in our brains, cue us for average rate of change. Okay, and then you're right, we sort of have slopes of what we call tangent lines, and that would be more like the instantaneous rate of change. Okay. Yeah, and so all of this is to say that when we have instantaneous rates of change, we actually call those derivatives. All right. And in a lot of our thinking, we consider, okay, what happens when things get really close to each other? Or what happens when things get really small? And so that's sort of a new layer to our thinking. And in terms of the derivatives, we've learned a ton of rules. And so maybe we could list off a few rules that we know about how to find derivatives. What are some of our most, let's start this way. What are some of our most hated rules? Which ones do we really dislike? Let's throw those under the bus first. Chain rule. Chain rule pain. All right, so we've got product rule. We've got chain rule. Oh, that implicit, definitely. All right, power rule, quotient rule. I love it. I love it. Exponential, sum and difference. So sum and difference, exponential. Maybe we could lump on the logs there. Yeah. Okay. you don't like it with the quotient rule. Yeah, I could see that. Okay, I wonder if someone could maybe type into the chat real quick, how do we know when we use product rule? Right? How do we know when we use product rule? It's not meant to be a trick question. Okay, yes. When there's multiplication, right? When there's multiplication, yeah. When there's a product, exactly. Exactly. Okay, and then so similarly, we might think we need to use quotient rule when we see things that are divided by each other. Okay. How about implicit differentiation? How do we, no worries at all. How do we know if we need to use implicit differentiation? Like, what's a really good example of when we might need to use implicit differentiation? We see a variable that represents a function. Yeah, we need the derivative of y. Okay. A lot of times I think about implicit differentiation and I think about the cases where the x and y's are mixed together. So in other words, like those questions where the x's and y's are kind of stuck together, it's really hard to get the y all by itself. That would be a really good time to use implicit differentiation. Okay. What about chain rule? When do we know we need to use chain rule? A function and a function, two functions 13. When we have a function inside of a function, when there's an inside function and an outside function, exactly. And so I wonder if we sort of made a note here about chain rule. Let's say I had some function like natural log of x versus the natural log of the square root of x. Which one of those, the one on the left or the one on the right, do we need to use chain rule for? So if we look at natural log of x versus natural log of the square root of x, yeah, I would agree that this one requires chain rule. Okay. What if we had cosine of pi x versus sine of x? Which one of those would I need to use chain rule for? Okay, I see one vote for the one on the left. Is that something that we all agree on? Yeah, exactly. We see that pi x. We could even maybe highlight that this pi x and this square root of x are sort of the inside function. And I know that one thing that kind of trips us up is like sometimes we take away the functions and we just call it like an f or a g. And so if we had one like this, f of x squared versus g of sine x, which one of those would require the chain rule? I see one vote for both of them. What do other people think? Okay, so 2 votes for both of them. And yeah, if we go back to the first few examples, this one has an inside function of the square root of x and an outside function of natural log. This one down here has an inside function of pi x and an outside function of cosine. But in both the f and the g, check this out. I've got an inside function here of x squared and an outside function of f. I just don't know what the f is, but I'm doing something to the x squared, okay? And if we use similar reasoning for the g one, we've got g as the outside function and sine x as the inside function. Okay. So in a nutshell, that's maybe some of the highlights of, what we've learned over the course of the last 9 weeks together, all right? I would, as you're preparing for this exam 3, make sure that you also still know how to do all these derivatives. Okay, so all these rules, making sure that you still know how to do a derivative is going to be really important on this exam. All right. So what's new? All right, so we spent the whole first half of this talking about slopes. And what we're about to embark on is we're going to actually start to look at area. Okay. And area is also going to have a major glow up, just like slopes did. We're going to take a look at area in so many different ways. We're going to think back to all of the formulas we knew from geometry. Those are going to be important. We're going to think about, so let's write some of these down. We need to know some of our geometry formulas. All right. What else are we going to need to know? We're going to need to know stuff about 2D shapes. And we're also going to take a look at some 3D shapes. All right. And the 3-dimensional piece is really going to come into play in Unit 5. Okay. So we're going to take a look at some geometry. We're going to take a look at some 2-dimensional and 3-dimensional shapes. And then for sort of all of these, we're going to learn how to find area and volume of different shapes. Okay. Yeah. And if we kind of go back to this idea of position, velocity, and acceleration, okay, that's what we learned before. Now what we're going to be focusing on is, well, if someone gives you the acceleration, how do you find the velocity? And if someone gives you the velocity, how do you find the position? Okay, so we're in other words, all this stuff that we learned, in the first half, we're going to focus on some of it, all right, not all of it, some of it, and how do we go backwards? How do we figure out where these functions came from? Okay. So with that being said, let's go ahead and get our brains working again with some derivatives, okay? And thinking about derivatives and the functions that they came from, and think about this in sort of a intuitive way, okay? So we've got a little chart right here, all right? And so what I'm going to have you do is in breakout rooms, there, let's see, 1, 2, 3, 4, 5 questions. Okay, so 5 questions. In your breakout rooms, I'd like you to go ahead and determine if this is the function, then what is the derivative? Okay, some of these you're going to do really quick, but where I'm really hoping there's some good conversations in your group is particularly around these last 3. Okay, so we're just going to go out into these breakout rooms for maybe about 7 minutes. Okay, and when we come back, we'll just share out some answers, make sure we're all good to go with those before we figure out how to go backwards. All right, so all right. So you're going to go into your breakout rooms. Let me make sure that I've changed the screen sharing settings first. before I do that.
Negative sign.
resume the recording. Here we go. All right. So before break, we thought a little bit about how to go backwards. And for some of us, it was kind of intuitive. But I think for others of us, and also as things get a little bit harder, we want to make sure that we have some rules to kind of go back to, okay? And so when we're looking at a few rules here, all right, one of the ones that I want us to walk out of here feeling really confident on is this power rule for integrals, okay? So just like we have a power rule for derivatives, there is a power rule for integrals, and it simply tells us how to go backwards from, you know, here's the derivative and how do we figure out what function it came from. Okay. Now, one really important point here, this is only when the power does not equal -1. Okay, so only use when power of x is not -1. Okay. And so if we kind of do a few quick examples here, the rule looks very intimidating, but let's do this. All right, so this is a new symbol for us too. So I want to take some time to talk about this symbol here. All right, that symbol is called an integral symbol. Okay, so this is the integral symbol. Right. It kind of looks like an F, but without that middle line. All right, so it might be fun to kind of practice writing some of those. You can do kind of like this or like this. Okay, and that's the integral symbol. What else is important about this? This dx at the end goes hand in hand with that integral symbol. And so if you have the integral symbol, you also need to have a dx. All right, and we'll talk a little bit about why we have that dx on Wednesday, okay? Yeah, you could think about it that way, okay? But when we are looking at the middle part, which is the part that tells us what we're taking the integral of, so in this part, or in this question, it's x to the n, all right? We call that the integrand. So the thing that is being taken, or having the integral taken of it, is called the integrand. Okay. So a lot of new vocabulary, but let's kind of practice the process here. So if I have the integral of x to the 7th dx, okay, so remember, if I have that squiggly symbol, I have to have the dx at the end, then I might notice that my integrand, this x to the 7th, is x to some power. And more specifically, that power is not -1. And so as soon as I notice that, I say, hey, if I want to find out where this function came from, I can take the integral or the antiderivative of that function. And so let's think about this. If I have x to the 7th, what was the power of the original function? Okay, if I have x to the 7th as the derivative, what was the power of the original function? It was 8, okay? And look at this. This is exactly what the rule tells us, that x will now be to the power of n plus 1, or in our case, 7 plus 1. So my integral is going to be x to the 7 plus 1 over n plus 1. So over 7 plus 1. Don't forget that plus c. Okay. Now, if we simplify this, we'll get x to the 8 over 8 plus c. Okay, that's one way to write our answer. Another way might be 1/8 times x to the 8 plus c. Okay. And I just wanted to take the moment to write both forms because I know that fractions can be really scary for us sometimes, and we might forget that something like this, x to the 8th over 8, is the same thing as saying x to the 8th times 1/8. Okay, and so I just wanted to put that in there to remind us. All right, does that kind of make sense how to use that power rule for integrals? So instead of subtracting a power, this time we add a power. And instead of bringing that power down, we have to bring that reciprocal of the power down. Okay. Right. So another important rule, yes, Ethan, that's exactly correct. We're going to do the inverse of what we did to get the derivative. Exactly. Okay. Yes, reverse engineering, that is exactly what we are doing. Okay, and so one of the properties that is important for us to know here is just like, and I think it was Christina who said that we knew a sum and difference rule for derivatives. It turns out that we have a sum and difference rule for antiderivatives as well. All right, so sums and differences. If we have plus minus something, we can just take the integral of each part and then add them together. And then this one is actually incredibly useful, which is when we have a constant multiple. And here k stands for a constant. I can go ahead and factor out that constant and then take the antiderivative. So these are all fun rules to know, but let's maybe do two quick examples here before we move into the other practice. Okay, so let's sneak one example maybe over here. That if I have the integral of, let's see, x squared plus 1 over x dx, okay. So what this sum and difference rule says is I can split this up to be the integral of the first one plus the integral of the second one. Okay, so we can see here that this plus here means I can split them and add them together. That's a very handy thing to know. And what rule would I use to find the antiderivative of x squared? So how would I find the derivative, or not the derivative, the antiderivative of x squared? We would use that power rule, okay? And so we would get x to the n plus 1 over n plus 1. So that's the first one, plus, where did this function come from? Like, what is the original function if that's the derivative? Yeah, this came from natural log. Also, what is the power for the x here? Maybe let me write that a little bit bigger, give myself some space. 1 over x dx. What is the power for the x? yeah, this power is 1, but if I were to rewrite it because it's in the denominator, this is really saying the integral of x to the -1 dx. Okay, and so I picked this one on purpose because anytime we see that that power is -1, that's the one time we cannot use the power rule. Okay, that is the one time we do not use the power rule. And so instead, we want to think, when that power is -1, nope, it's just -1. That is the one and only exception. Okay. -2, we use the power rule. -3, we use the power rule. -2/5, we use the power rule. Exactly, because if we use the power rule, we'll get a denominator of 0, and that's undefined. And so we have natural log of x. And then we want to remember our plus c at the end. Okay. And so altogether, we would get 1/3 x cubed plus natural log x plus c as the antiderivative. Okay. So that's an example of the sum and difference rule. All right, and let's squeeze in an example of the constant multiple rule. Okay. So let's say that you had an integral of pi cosine x dx. Okay. What's my k value here? What's the constant that I'm multiplying in? Yeah, it's that pi. And so what this rule says is that we can go ahead and bring the pi out in front of the integral, and then just figure out what the antiderivative of that piece is. And so I think we know that if the derivative is cosine, it came from the original function of sine. And so we'll get pi times sine x plus c. All right, so all we've done is take that constant out, then taken the integral, and then multiplied it back in. Okay. So let me pause here for a moment. We've kind of talked about two fairly juicy examples here. Are there any questions so far? Well, let's think about this. So the derivative of sine is cosine. So where did cosine come from? It came from regular sine. Right? The derivative of sine is cosine. Yeah, yeah. And that's where things start to get tricky, is like, is it positive? Is it negative? And to answer that question, the better you know your derivative rules, the easier it is to kind of go backwards, okay? All right, so we've got a few examples here to kind of take a look at. And so what I'd like to do is go ahead and give you maybe about 3 or 4 minutes just right here. Let's work on questions 1 through 4, okay? And as you work through them, you're welcome to send me a message directly for like answers. That's totally fine, just to say, hey, is this correct? But let's kind of work on our math here, get a little bit of this independent practice time, applying some of those rules that we just took a look at. And in about 4 minutes, we'll check over those answers. Okay, so I'm going to stop talking for a little bit. You folks are going to try your hand at some of these rules, and then we're going to share out our answers and make sure that we understand the process behind what it is that we're doing. Let's take maybe about another 2 minutes. If you are done with these, there are more practice problems on the next page, all right? So take maybe about 1 to 2 more minutes. I did reach out to some of you directly to see what answers you got. You're also welcome to send me potential answers that you have. All right, so let's take a look at some of these questions, okay? Now, so far, other than like the opposite of the derivatives we know, the one rule we really know is the power rule, okay? And so as such, sometimes it is helpful to think about what is that power and writing it out so that you can see the power. Because once you see your power, as long as that power is not -1, then you can go ahead and use this power rule, okay? And so let's take a look at example number 1 over here. If I were to rewrite this so that I could see like x to some power, what would the power of x be? X to the 0. Okay, so it's one of those sneaky messages sorry, sneaky numbers where like you're supposed to know that it's a 0, but nobody writes it. So then sometimes it's easy to forget that. Okay, but if we were to think about the power rule, okay, the power rule and that constant multiple rule, so I can go ahead and take the 5 and bump it out to the front. So I get 5 the integral of 0 to the or x to the 0 dx. Okay, and now I can use the power rule. So 5, and let's see, we'll get x to the 0 plus 1 over 0 plus 1. Don't forget the plus c. And so when we clean this up a little bit, what do we get? 5x plus c, perfect. You get 5x plus c, and that is our antiderivative of 5, okay? All right, now, can someone help me identify what is the power that I should be writing for example number 2? That power is 1. Good, good. Okay, so since we know that power is 1, we are in the clear to use the power rule. So we get x to the 1 plus 1 over 1 plus 1 plus c. And when we clean that up, we should get x squared over 2 plus c. And what is another way to write x squared over 2? One half times x squared plus c. Good. Okay. Now, some of you will say, I just want to write one fraction because that's easier for me to see. And some of you will be like, I want to see the fraction in the front. All right. And regardless of which one you choose, it is likely that your Calc 2 instructor, your Calc 3 instructor will all have sort of different ways of writing it, either the first one or the second one. So it's kind of important to be able to know that they're the same, okay? All right, so far we've got our power rule. All right, what rule might we want to use for example 3? Indefinite integrals is not the name of a rule. Okay, so let's make sure we know the names of the rules. Yeah, that constant multiple, all right, that constant multiple. So there's one in the green right here. We want to use that constant multiple rule, okay? And so our constant here in this case is the 2, kind of like we had a pi in that example above. And so we could rewrite this as 2 times the integral of sine x dx. And let's think about this. Where did sine come from? I think we had this in one of the previous examples. It comes from negative cosine. So it's like 2 times negative cosine plus c, or we tend to just bump that negative sign all the way out to the front. And here is our solution. Okay. All right, we've got one more over here. What rule or rules might we want to use for example 4? Power and I think you meant constant. Yeah, we had a constant of 4 and our n value is 3. Good, good. So if we sort of bring that constant out, we'll get 4 times the integral of x cubed dx. And when we plug that into the power rule, we get 4 times x to the 3 plus 1 over 3 plus 1 plus c. And let's see, we get 4 times x to the 4th over 4 plus c. Now, I'm going to be kind of sad if we choose to leave our answer like this, because I think there's a pretty short simplification we can make here to make us write even less. What is that simplification? Yeah, those 4s cancel out. I got 4 on the top, 4 on the bottom. All I'm left with is x to the 4th plus c. Okay, exactly. We want to make sure we reduce. All right, so we've got these 4 examples here. Let's see, can we generalize and say if kn equals n plus 1? Yes, exactly. Yep, that's a really great generalization. Okay. And I would encourage you to use generalizations only when you feel like you've really internalized those. And until then, maybe it's best to write things out the long way for a little bit, just to make sure that you get that kind of practice in your head. Okay, perfect. All right, let's go ahead and move on. So we've got 4 more practice problems here. All right. And again, let's take a few moments to kind of sit and work through these on our own, all right? And you might have to go back and look at some more of those rules that we learned when we were taking derivatives. Now, if you made a reference sheet for exam 2, that's probably pretty handy here. But remember, we need to think about how do we write these powers? Like, what are the powers that nobody writes for us that we have to know are there, okay? And as you're working through, feel free to send me a message and say, hey, is this the right answer? I would happily give you a, yes, this is correct, or a almost, let's make these small changes, okay? And I'll do the same thing. I'm gonna reach out to a few of you to see what you get for these answers. Getting a lot of great answers being sent over, great questions being sent over. So keep up the good work. All right, folks. Well, lots of great work and thinking being done right here. Some of us definitely doing some great stretch thinking, going back to some of our notes from chapter 2, or rather chapter 3. I love it. I love it. All right, so let's take a look at example number 5, okay? So for example number 5 here, we can use that constant multiple rule, that 2, we can bump right out to the outside, and we'll get -2 the integral of x to the first power dx, okay? We can plug that into our power rule. We get -2 times x to the 1 plus 1 over 1 plus 1. Don't forget our plus c, making an effort to make it a capital C if we ever want to interact with WebAssign. Otherwise, it doesn't really matter. And when we simplify this, we'll get -2 x squared over 2 plus c. And again, this is maybe a place where I'd be a little disappointed if we left our answer this way, because there's one small simplification we can make. And that would be just like above. We can reduce this 2 and that 2, and we'll end up with -x squared plus c. Are there any questions about using that power rule right there? That's going to be one that's really fundamental for us. Okay. All right, now for example 6, when we look at example 6, we might notice that there is a sum here, which allows us to split into 2 different integrals. And so we could write this as the integral of 3 cosine x dx plus the integral of secant x tangent x dx. Okay. All right. And when we further simplify here, we might notice there's a constant that I can pull out here. So I get 3, the integral of cosine x dx, plus the integral of secant x tangent x dx. Now notice this 3, it only goes with the secant, or sorry, with the cosine, okay? The 3 does not apply to that secant tangent part. The 3 only goes with the cosine part, okay? And so what do we get when we take the integral or the antiderivative of cosine x? Three sine x, good, good. So we get 3 sine x plus, now this one looks kind of scary and gross, so let's go back to our list of derivatives. What function had a derivative of secant tangent? Secant x, good, good. Okay, so that means the antiderivative of secant tangent is just secant. And don't forget our plus c. And there we go. Okay. All right, moving on to example 7. Now, example 7 I thought was a little tricky. And I really love that the folks that I reached out to did one really clever thing before they took the antiderivative. And that is they rewrote this integral. In fact, they rewrote this integrand. How might someone rewrite 1 over x to the 43rd before taking a derivative or before taking an integral? Yes, I love it. X to the negative 43. All right. Okay, now, just like when we were taking derivatives, we got to rewrite it so we see that power. Now we can apply the power rule for integrals. And so that will give us x to the negative 43 plus 1 over negative 43 plus 1 plus c. And if we add very carefully, we'll get x to the negative 42 over negative 42 plus c. Okay. And let's talk about some ways that we might rewrite this particular integral. Right? What are some ways we can write this? Negative 42 over x. All right, what are our thoughts on that? Negative 42 over x plus c. Valid, not valid? What are our thoughts? Right, there's so many rules about powers. Okay. Yeah, so we can't, I like that we're moving things, okay? But let's be really thoughtful about what we're moving. Anything that has a negative exponent, okay, not just a negative, but a negative exponent, that gets moved. And we still have to keep the power there, but we want to make sure that it's now a positive power, okay? But this 42 right here, it has a negative, but it doesn't have a negative exponent, so we're going to leave it where it is. All right, so I'm going to keep this negative 42 on the bottom. Okay, so this could be one way to write it. You might also see someone write this as negative 1 over 42 x to the 42 plus c. So someone might just pull the negative sign and put it right in the front of everything. That would also be okay. All right. But we want to be really careful that we know what gets bumped to the other side of that fraction line versus what actually stays where it is. Okay. All right. We got one last question over here. And for that one, I thought that was maybe one of the tougher ones on here, okay? So here's the thing. When we use our power rule, we need to be really careful about applying it. And the first thing we want to do is always think, is this a derivative of some function, okay? And so in particular, after we take this constant and we pull it out to the front, we get 4. The antiderivative of 1 over x squared plus 1 dx. Okay. Now, let's think back into our notes. Is there anywhere where we saw a derivative that was 1 over x squared plus 1? Right. Where did we see a derivative that was 1 over x squared plus 1? There we go. There we go. All right, that is an inverse tangent. And so when we take our integral or our antiderivative, we'll get 4 times inverse tangent of x plus c. Okay. This one we're going to see a little bit in Calc 1. Okay, so we're going to see a little bit of this in Calc 1. But for those of you who are moving on to Calc 2, or planning to move on to Calc 2, we use this one in Calc 2 a lot. Okay, so this definitely comes up a lot in Calc 2. And so I want to make sure, like, of all the different trig ones, like which ones kind of come up again. And this one right here is definitely one you want to sort of have in your back pocket for Calc 2. Okay. All right. Before we move on to this last section, I'd like you to do me a favor. You're going to send me a message directly, just to me. All right. You're going to type in a positive one if you're like, this is easy. I got this. It makes total sense. All right. If you are like, it kind of makes sense, but I feel like I should do a lot of practice with this, that's a 0. And if you're like, I have no idea what we're doing here, that is a -1. All right, so just type in a number, 0, 1, or -1. Okay, this is good, this is good. Waiting for a few more responses out there. right. So going to drop a link in the chat right now. I see a lot of, I would say we're probably about on average like a 0 in this class right now. And so I think some of the hardest things about looking for practice problems is that sometimes the practice problems just give you the right answer, but if you got the wrong answer, then you don't know what you did wrong, okay? And so let's go ahead and I'm gonna drop this link in the chat, all right? I've talked to some of you about this website before. This is Paul's online notes, okay? One of my favorite things about this website is that he gives not just your answer, but he gives you steps to get to the solution, all right? And so what I'm hearing from a lot of you is that extra practice would make this better, all right? And so one of the things that you can do is go through, and he's got a bunch of practice problems, like at least 50 right here that I'm looking at that all have worked out solutions, okay? So this can be a place for you to kind of go and practice the different rules so that you can feel like we're all getting a little closer to that 1 and not as close to the 0, okay? All right, so if you haven't opened that page yet, I would go ahead and open that link, maybe bookmark it for later, but he's got a bunch of stuff that I think is valuable for practicing, okay? All right, so we're gonna finish off today with something called initial value problems, all right? Initial value problems. And so what we're going to be doing here in these initial value problems is finding that plus C, okay? So that plus C at the end that I've just been like, I want you to write down a plus C. We don't really know where it came from, but sometimes we get to problems where we do have enough information to find that plus C, okay? And so let's take a look at this particular problem. So we've got car A is traveling at 1 rate and car B is traveling at a different rate. All right, so car A is going 88 feet per second and car B is going 44 feet per second. They both slam on their brakes at the same time. And their brakes work the same exact way. My question to you is, which car stops first? So we got car A, car B, they're driving down the road. Maybe they see like a squirrel crossing the road. I don't know, they always seem to do that at inopportune times. They slam on their brakes. Who's gonna stop first, car A or car B? Okay, we've got 2 votes for car B. I would agree. I think car B is going to stop first, right? How come car B is going to stop first, though? Like, why does that make sense to us that car B would stop before car A? It was going slower, right? It was going slower to start with. And so it's going to take a shorter amount of time to get down to a speed of 0. Okay. And so what we're going to find out, though, is exactly how many seconds it's going to take car A to stop and how many seconds it's going to take car B to stop. Okay, so intuitively, we know that car B is going to stop first. But if we want to make this more specific, then we can think about using some of the stuff we've learned to actually figure out what's happening, okay? Now, at the very beginning, we wrote down something about position and acceleration and time. Let's see. Oh, right here. So I have position. Someone remind me how I get velocity from position. How do I get velocity from position? Yeah, I take the derivative, okay? And how do I get from velocity to acceleration? Yeah, we take the derivative again. So guess what happens when we go the other way? If I have acceleration and I want to find velocity, I'm going to take the antiderivative of acceleration. That will give me velocity. And when I have velocity, if I take the antiderivative of velocity, I will get position. Okay, so just like if we have position and we want to find velocity and acceleration, we can also work our way backwards and find velocity from acceleration and position from velocity. That's a good question. How do we type the integral symbol? I guess for right now, you could maybe type in int. That suffices for an integral symbol. Yeah, it does get trickier, right? When we have sort of more math symbols. Okay. Ooh, fancy. How'd you get that? Option B. Ooh. Yeah. So if you have a Mac and you type in option B, it should give you the integral symbol. Yay, that's awesome. Good find, good find. Okay, so let's get back to this problem, okay? So we're gonna take a look at car A first, and then we'll take a look at car B. So for car A, we know that it is decelerating at a rate of 15 feet per second squared. And so what we can say is that the acceleration of car A is negative 15 feet squared, feet per second squared. Okay, so they've given us our acceleration function. And from here, how would we set up our velocity function? Well, we could say that is going to be the integral of a of t dt. And when we plug in the function, we'll get the integral of negative 15 dt. All right, so let me just pause there for a moment. Are we okay with what just happened on the screen? We've got velocity. We got that as the because it is decelerating. So the acceleration is negative. Yeah, that's why it's negative. Okay. Okay. So now our goal is to find our antiderivative. So if we find our antiderivative of negative 15, what do we get? Negative 15, and let's just change that x to a t just because we're using time as our variable here, but exactly negative 15t plus c. Now here's the beauty of this. We can actually find out our c value, okay? So to find c, we're going to use our initial condition. Okay, and so the initial condition here is at the beginning of when we started measuring things. How fast was car A going? So if you go back into the problem, how fast was car A going? Yeah, 88 feet per second. So here's what we're going to do. Everywhere where we see a T, we're going to plug in 0. And everywhere we see a V of T, we're going to plug in 88. And so when I write that out, I'll get 88 equals negative 15 times 0 plus C. Now this is really nice because the only thing I don't know is C. So C equals, let's see, negative 15 times 0 is 0. So C equals 88. Now that's not our final answer though, okay? So what we want to take a look at is this. How many seconds elapse before car A stops? So if I have my velocity function equals negative 15t plus 88, and I want to know when the car is stopped, what value can I substitute into this velocity function? What do we know about when things are stopped? Okay. This is a really important connection here, that when the velocity is equal to 0, right? When the velocity is equal to 0, that means that the car is stopped, right? That's something we learned in the last few weeks, the last few months. If we have something at rest, then that velocity is going to be equal to 0. We can solve for t now, and I believe we get 88 over 15 seconds. So it's going to take car A 88/15 of a second to come to a stop. Okay. Well, let's do something similar for car B. All right, so we're going to do the same thing again, but we're going to modify. We're going to see what do we change for car B and what stays the same. Okay, so let's start with this first line, the acceleration function. Is the acceleration function the same for car A and car B? The acceleration, yes, right? They both slam on their brakes to try and miss the squirrel. So we get the same negative acceleration, okay? All right, well, what about this next line? Is this part the same? Is the velocity part, like when I integrate it, is that going to be the same or is it going to be different? But up until here though, like before I find my C, are they the same? Okay, so this part is the same. So I can say that the velocity equals the antiderivative of the acceleration, which is the antiderivative of negative 15, which gives us negative 15t plus C. All right, now let's look at what we did next. We found C using the initial condition. Okay, so to find C, use the initial condition. What is our initial condition? Same or different? Right? Is our initial, yeah, it's different, right? Car B is going at a different speed. So we can say V of 0, it's not going to equal 88, but our V of 0 should actually equal 44. Okay. All right, so we plug that in, we get 44 equals negative 15 times 0 plus C. And this time we get a C value of 44. So Ethan, you were correct. Our C value is different, but everything else was the same. Like the process was the same. We just put in a different initial condition. Okay. Now we want to know how long it takes for car B to come to a stop. Can I still set my velocity equal to 0? Like, is that part still okay? It is still okay because we're looking for when it comes to rest. And so we'll have negative 15t plus 44, because again, this is talking about when is the velocity 0 or when is the car not moving anymore. And when we solve for t, we'll get 44 over 15 seconds. And so we can see now that car B does in fact stop first. It only takes car B about 3 seconds to stop, whereas it takes car A maybe closer to 6 seconds to stop. Okay. So not only is this a initial value problem where we get to practice finding our C value and then plugging it in, but it's also a chance for us to think about like the idea, like why would we be interested in going backwards from slope, is that sometimes it tells us, you know, important information like this. We might not have distance information, but we might have velocity information. Or we might not have velocity information, but we have acceleration information, and we can use that to find different things. Also, this is a plug for driving safely and making sure that you were within the speed limit that is designated for your area, because it literally could take you twice as long to stop. Poor little squirrel. Okay, if we're looking at the car, would be going for 20 feet per second. We would say V of t is equal to 20. Yes, if that's a 20 in your second one, then yes. Yes, exactly. Exactly. All right, folks. Well, we are going to stop. I know. I see what you did there. Okay, so we're going to stop recording right now.